Ngalakin Khadijan Nyunga Boja.
Video 10, types. So today it's a rather technical topic and fairly dry, so we'll just get through it as quickly as possible because it is unfortunately very important. Types refers to the kind of data that is going to be stored in each column. In particular, when we create a table using the create table command, the database designer at that point has to specify what is the name of the column and also what is the type of the column. So the type indicates to SQL what kind of data will be stored there. Is this column going to be used to store numbers? For example, in the AFL example, the home score was just a number. Is the column going to be used to store strings? Is it going to be used to store Boolean values, and so on? Now, there's many good reasons why SQL might like to know in advance what kind of data is going to be stored. One of those reasons is that it allows efficient allocation of disk or memory when storing a table. If SQL knows that a particular column is always exactly 8 bytes long, then it can just store all of those values in one contiguous block of memory and can very rapidly recover any particular value. Knowing types allows SQL to be sure that the operations that the user has asked for actually make sense. So that's a form of data integrity. If you've got an expression in your SQL query that tries to add a string to a Boolean, well, there's no sensible way of interpreting what that means. And so a SQL server in that case should say, type error in this operation or something like that. Usually that will mean that the user has really got confused about exactly what types of things are being stored. The type system also allows certain types of polymorphism. So, for example, plus can be used to add to integers. It can also be used to add to real numbers, and so on. The type system will allow SQL to understand what the operation actually means based on the types of the things that it's operating on. Okay, so let's consider an example. Let's consider a field for storing a unit code, like CITS1402. Now, at UWA, unit codes are standardized, and so they are always exactly 8 characters long. And there's going to be, so from here to here, that's the extent of the actual unit code, and it's a mixture of alphanumeric characters. So CITS are alphabetic characters, 1402 numeric characters. Right, in SQL, like not SQLite, but in SQL the standard, you would normally expect to declare this column as follows. You would give it a name, unit code, and then you would tell SQL to use a field that is 8 spaces wide, each of type char. So char stands for character. So that would put aside exactly 8 characters for each of the values unit code. At UWA, the unit codes are always exactly 8 characters. And so this will then provide a very efficient way of storing the values in this column. It can set aside exactly 8 bytes, and all of those 8 bytes will be used. Okay, so that's a good use of like the type system. Okay, the name of a unit, on the other hand, doesn't have a standard length. So some units have long names, like relational database management systems. Some units have short names, like network science. How should we declare a variable used to store some value whose length we don't know in advance? Well, in SQL, this is the sort of recommended way of doing it. So varchar means variable length string of characters with maximum length 64. Okay, so then SQL knows that it has to set aside enough space to accommodate maybe up to 64 characters. So how will it do it? How will the system deal with fields of type varchar? Well, there's sort of two options, really. One of the options consumes space, like wastes space, and one of the options wastes time. So the first option would be to allocate exactly 64 bytes for each unit name. So it would allocate a block of memory 64 bytes long. When you store a particular value in it, network science, I'll make it a bit longer. So here we've used 64 bytes. We've allocated 64 bytes. The first few bytes are used in storing the name, network science, and the remaining bytes are just junk. They're not there. Now, that is wasting some space, but it's actually very fast to access those values because the system knows that, like, after 64 bytes, it moves maybe to another 64 bytes with the next name in it and with the next name in it. Okay, so here we're wasting a bit of space, but we can get very rapid access to that field. Alternatively, the system can decide that space is important, in which case it's going to use exactly the right amount of space for each of these things. So it's going to have to use exactly the right number of bytes for network science, and then more bytes for the relational database network systems and so on. This picture is intended to just show like the computer memory being allocated to store these values. Okay, so now we haven't wasted any space because we've only got a short chunk of memory used for short names, and we've got a longer chunk of memory used for longer names. But this now means that we don't know exactly where any particular field starts. And so somehow we've got to manage the location of each value. We've got to decide that the 25th unit name doesn't just start at position 25 times 64, but you actually have to work out how long each of the previous strings are in order to find the value in memory. Okay, when SQL was young, this is the 70s, SQL started, disk space and computer time were both scarce, and whether one or the other was more important would keep changing. Like there'd be some advances in disk technology, and then there would be advances in CPU technology, and so on. Basically, it was necessary for the programmers of the day to have very fine-grained control over what we now consider to be rather low-level issues. So then it really made a difference whether you stored something as char 8 or varchar 64, and therefore there had to be a mechanism for allowing either way. Okay, let's continue. Suppose we now want to add another column, and that's going to be the unit description. Now, the unit description can be very short, or it can be very long, many paragraphs of discussion. If you look at the unit descriptions on handbooks.uwa.edu.au, you will find some units have quite a terse description, some have quite a long description. Okay, the right type in SQL to store an arbitrarily long sequence of characters, just a pile of text. So that would be something like, this unit is concerned with the theory and practice, and so on. And it could go on for several paragraphs. Okay, so here there's no sensible value that we can use for the maximum length of a unit description. And so we just use the type text, and we let the system sort out how it's going to store and retrieve values of that type. from that column. Similarly, in modern implementations of SQL, like MySQL, for example, then there are lots of different ways of storing integers. You can declare an integer to be, you can declare a column to be of type integer, or of type int, or of type tiny int, or of type medium int, or of type big int, and so on. So these differ in the amount of storage space that MySQL will allocate for them, and therefore the range of values that they can store. So I can't remember the exact numbers, but it's maybe tinyint only uses 8 bits or 1 byte. Well, that would only give us the values from, so if we've only got 8 bits in our storage space, then we can only store 2 to the 8, 256 numbers. So a tinyint would be used for storing only values that were maybe from 0 to 255, or maybe from minus 127 to plus 128. Medium int would be used for storing bigger integers, and big int would be used for storing even bigger integers, and so on. Okay, so if you read SQL or look up SQL, other SQLs, like Postgres, MySQL, and so on, you will see a plethora, a very large number of different types. And they all seem to do, well, something that's really very subtly different from the other things. On the other hand, if you get the types wrong, then things will mysteriously go wrong, but you won't understand why. Because in some situations, the value of an expression will actually change depending on the types of the arguments. The simplest example of this is if you declare something to be, say, tiny int, you might want that to be like the number of points that some student has obtained towards their degree. Well, a tiny int with 8 bits can store values from 0 to 255, and no degree has more than 144 points, and so you're okay. But suppose things suddenly change and UWA decides that from now on we'll have each unit being worth, all the point values are doubled. So then all of a sudden you'll have degrees that can have 288 points. Well, if you do that calculation using tiny int, then you will get mysterious results, because if a value overflows, it doesn't throw an error, it just cycles round the values. Okay, anyway, I don't think I explained that well, so please, you can forget that. It's not so important. Okay, in computer science, a system or language is called strongly typed if the system enforces the types to be correct. So here's an example, here's a little example from Python. I've tried to do an addition, and I've given it as an argument a string, the string containing the 1-digit 2, and 3, the number 3. So this is a string plus an integer. String plus integer. Now, in general, there's no sort of unambiguous way to understand what someone might mean when they add a string and an integer together. So if the language is strongly typed, it will just say, this doesn't make sense, I'm going to give up and throw an error. Okay, and so it does throw an error. If, on the other hand, I add together 2 integers, 2 plus 3, then I get 5. If I add together 2 strings, the string 2 and the string 3, then it just concatenates the 2 strings, so I get 2, 3. Okay, so the point here is that Python understands what it means when you try to add together 2 strings. It understands what it means when you try to add together 2 numbers, but if you try to add a number to a string, it says, I can't do that, and it gives up. Okay, basically the assumption here is that if you ask for a string to be added to an integer, then there must be an error because string plus integer is it's not properly defined. Okay, a system or language is weakly typed if it's more permissive about this. And that means that it will try its best to interpret the statement in some sensible way. So even if the arguments don't really match, it'll sort of try to guess what the user really wanted. Okay, SQLite is weakly typed. So it will try its best to find a sensible interpretation of the input, even if it doesn't make complete logical sense. So here we've added together the string 2 and the integer 3, and it has decided to just treat that 2 as an integer. It just converts it to a number, and then it does the operation as a number, and it produces the numerical value. Okay, so SQLite is weakly typed. It won't throw up errors that tell you that that the operation, the operands, the two arguments, have the wrong type. Let's see a little bit more about what it does. I mean, it does seem fairly sensible that if you have a string which just happens to be all numbers, then you might as well treat it as a number. What else does it do? Well, suppose I add together two strings, 2 plus 3. Well, Python, we saw, decided that the correct way to add strings together was to concatenate them, to glue one to the end of the other. SQLite, on the other hand, decides that both of them should be converted to numbers, and then it will do the numerical operation. What about select 2 plus A? Well, I want to emphasize here that when I say A, this is the literal string value, A, like a string with one character whose value is A. It's not A without quotes, because A without quotes would be treated as a column name, and SQL will correctly say no such column. Okay, so 2 plus A. Well, now we're getting pretty silly, right? There really isn't, I mean, unless you're going to concatenate strings, there's no real sensible way to add the number 2 to the string A. Okay, but what SQLite does, if it can't interpret the string as a number, it just replaces it with 0. And then you just get 2 at the end of it. Okay, so basically SQL is doing stuff with types that we can't really predict in advance, and in some cases it makes sense, and in some cases it doesn't seem to make much sense. So what is the trade-off we're talking about here? And the real trade-off is, should the system protect the user from themselves? In other words, prevent them from trying to do calculations that are on the face of it not very sensible? Or should the system trust the user by saying, well, if the user's asked for this to be done, then they must have some genuine meaning in mind, and so let's just try our best to work out what that meaning might be. So, strong typing is safer. Strong typing is safer. It will only do an operation if the things it's operating on have the right types for the operation. The argument in favor of strong typing is, if the user is asking for the sum of a string and an integer, then that is logically flawed, and so we should prohibit it. We should protect the user from their own stupidity. On the other hand, weak typing is more flexible. So, I mean, sometimes integers are represented by strings. For example, if you type a number into a web browser, then the program will receive the number just as a string of digits. And so if the user does ask for the sum of a string and an integer, well, sometimes that does make sense. And so the system should try to comply. The system should trust that the user knows what they're doing when they ask for the sum of a string and an integer. Okay, so do you want safety or do you want flexibility? Personally, I prefer safety. I like languages that are strongly typed, but there are many people, clever people, and people whose opinions I respect, who like weakly typed languages. Okay, now having done that sort of short tour about all the, well, about the sort of philosophy behind types and some of the types you might find in MySQL and others, now we drop the sort of bombshell that it's all different in SQLite. So SQLite does things in a quite different way from any other SQL implementation that I know. SQLite has only 5 types. And in fact, there's only really 3 types that we are going to, well, 4 types that we're going to encounter. The first type is null type. The only thing that the null type can store is the value null. So this is really, it's really just a value and a type at the same time. Integer. A column declared to be of type integer can be used to store integers. Integers are whole numbers, positive or negative, so 1, 10, minus 23, and so on. Real. Values with decimal points are deemed to be real numbers, and so that's numbers such as 1.2 or minus 3.14 and so on. Or text. Text is just a string of characters, so relational databases or something like that. And final type is called a blob, which stands for binary large object, and that's essentially just a chunk of memory that just contains binary data, and the database has no interpretation of what that might mean. It's just storage, essentially. Okay, so, well, you might have noticed, of course, that when we declared the AFL table game, we had things that were not integers or reals or texts. What did we have when we declared the AFL table game? Well, we had game day, which was a date. Okay. Then we had home team, which was text. So we've seen text. So that was just a text string like, Fremantle or West Coast. We declared the scores, the 2 scores, to be integers. And we declared the playoff field to be a Boolean. And a Boolean, of course, is a type that takes on only 2 values, true or false. Okay. Okay, so what's happening? Why does SQLite allow us to declare things of type date and int and Boolean when it doesn't actually have those types? Okay, the reason is that things like date, int, and Boolean are very commonly used in other implementations of SQL. So what's happening here is SQLite has decided to, or the designers of SQLite have decided to make their system reasonably compatible with other versions of SQL, so that if you get a table from MySQL, for example, then you should be able to use it in SQLite without having to do too much fiddling around, changing everything. So SQL then allows any code to refer to these types that are not in SQLite, like Boolean and date and so on, but it silently treats them as one of its own types. So when you ask for a table to be of type Boolean, SQLite secretly changes that to integer and then just works as though that field were an integer field. if you want to find out what type a SQLite value actually has, then you can use the function type of, and that will tell you what type a particular value has. Okay, so select type of game day. So we'll choose, we'll take the first row of game, we'll ask for the type of game day, and then I don't want to do it again because they'll all be the same type, so I'll just have one row for the answer. And so the date field gets translated to a text field. The Boolean field gets translated to an integer. And then the things that were text, were declared to be text are text, and the things that were declared to be integer are integer. Okay. The only thing you really need to be aware of is that there's no true Boolean and there's no date type. Most databases have very sophisticated date handling facilities because databases are really heavily used for like keeping records of transactions that occur at certain dates and so on. There's also no true Boolean type. Okay, so how does SQLite manage Boolean values or Boolean expressions? Okay, so there are lots and lots of Boolean expressions in SQL, especially every time you see a where, there must be a Boolean expression afterwards. So here's a Boolean expression where home score equals 100. Now the ... just means that this is just a snippet of code. It's not a whole SQL query. You can put the brackets in, or you don't have to put the brackets in if there's only one. So what this Boolean expression will do is home score will be a certain value. So this is processed once for each row. It looks at the value home score, tests whether it's equal to 100, and it will return, well, it will evaluate to either true or false. But if SQLite doesn't have a Boolean, what value does home score equals 100 have? Well, it simulates Booleans by using 1 for true and 0 for false. So this Boolean expression, when it's evaluated, will have the value either 1 or 0. 1 is always going to be treated as true, 0 is always going to be treated as false. Here's another Boolean expression. Home score is greater than away score. So it's processed, it's examining a row. It looks at the home score value, it looks at the away score value. If the home score is strictly greater than the away score, then this Boolean expression has the value 1. If it's not, it has the value 0. Here's a Boolean expression where we're comparing, so the Boolean operator is less than or equals. We're going to look at home score minus away score. That's going to be the difference between the two scores, but it might be positive or negative because we don't know whether the home team won or the away team won. The abs takes the absolute value of that, and then it checks to see whether it's less than or equal to 10, and then it either has a value of 1 for true or 0 for false. And then here's a more complicated Boolean expression that uses a Boolean operator. So it evaluates this Boolean expression first, home team equals Sydney, that's either true or false, either 1 or 0, and then it evaluates this expression next, away team equals Sydney, that's either true or false, and then it checks the OR of those two values. Okay, so as I was saying, in SQLite, Boolean expressions simply evaluate to 1 if the expression is true, or 0 if it's false. Here's just a couple of silly little things just to show you how you can actually access the value of these Boolean expressions. So 1 plus 2 equals 3. That's a Boolean expression. It's going to calculate the 1 plus 2. That's a 3. It's going to look at the value 3 on the other side, and then it's going to ask whether the two are equal. Equal and equal are the same operator almost the same operator in SQLite. So it doesn't matter which one you use. The equals is sort of a a standard way of checking for equality in C, and seeing everything in the world is written in C, many people prefer to reserve equal for their booleans. On the other hand, if I ask whether 1 plus 2 is greater than 3, well then 1 plus 2, it's evaluated to 3, then it checks is 3 greater than 3, it's false, and so the value returned is 0. If you write SQLite code or read SQLite code, you might see true and false written in various places. Okay? True and false are just aliases for 1 and 0 respectively. So that means that if, well, it means two things. First of all, if SQLite is trying to use code that came from some other database that does have true and false, well, then it doesn't need to be changed. Conversely, if you're writing SQLite code that may be used in other implementations of SQL, well, then you can use true and false, and that will be one less thing that that needs to be changed when it's transferred. So you can use true and false to enhance the readability of your SQLite. If you've just got 1s and 0s floating around, then it's not maybe 100% clear what you're intending to do. If you use true and false, then it becomes explicit what you're intending to do. Or you may use true and false just for compatibility with other SQL implementations. Okay, well, that's probably enough on types for today. What you basically have to remember is that if you're writing pure SQLite, you can just stick to these types: integer, real, text. Null is a very special value that we'll discuss later. Blob is used for storing binary data like images and things like that, and we probably won't be using that at all. So integers, reals, or texts are the main things you need to remember.